Hi, I'm Maria, and I'll be talking about joint work with Matt Gormley and Taylor Berg-Kirkpatrick on deciphering informal romanization. In this talk, I'm going to describe the task of converting informally romanized text back into the original orthography of its language. This kind of romanization is used in social media, and it's not standardized, so each user makes their own character substitution choices. However, all of those choices are based on the shared perceptions of character similarity, which could be visual similarity between character shapes or phonetic similarity between the phonemes that the characters represent. And we propose incorporating those shared notions of similarity into the model as inductive bias. I will describe our unsupervised finite state approach, and we train our model on two languages, Egyptian Arabic and Russian. And for Russian, we collect and annotate our own dataset. Finally, we show that incorporating the mentioned inductive bias brings the performance of the unsupervised model close to that of the supervised one. Let us start with a motivating example. Messages like this one are common on social media, and they're typed in Latin characters, but identifying the language they're written in would be a challenge both for language identification systems and for humans. This particular message is written in Russian, a language that is usually represented using Cyrillic alphabet, but this particular user chose to encode it in Latin script, probably due to not having access to a Cyrillic keyboard. And our task is observing the sequence of Latin characters that the user typed, decipher the original alphabet sequence that they had in mind. Let us inspect the character substitutions used in this example in more detail. Many of them are phonetic, where for each source alphabet character, the user picks a Latin character associated with the most similar phoneme, like the Cyrillic P and Latin P here. Other substitutions are visual, where the Latin character is picked by having the most similar glyph shape. For example, the Cyrillic U and Latin Y here. This is especially easy for Cyrillic because it actually shares a lot of glyphs with the Latin alphabet, but the substitutions could be more complex, like when Arabic characters are replaced with numerals. It is more difficult than a standard substitution cipher. We can see in this example that the same Latin character can be mapped to two different original alphabet characters. And because there's variation between different users, we will also see the same original alphabet character represented with multiple different Latin characters. Because this kind of romanization is used when typing in native script is difficult, there's almost no natural parallel data for this task. So we're going to treat it as an unsupervised problem. And although there is variation between users, we're going to assume that the notion of character similarity is shared between different people and even different languages. And we hypothesize that encoding this shared notion of character similarity into the model as inductive bias can compensate for the absence of actual human supervision. We propose a noisy channel model where we observe a Latin alphabet sequence L and need to predict the original alphabet sequence O. And the probability of the Latin sequence is factored into the transition and emission probabilities and marginalized over all possible latent original alphabet sequences. Besides that, we have a prior on the emission parameters, which is how we encode the inductive bias into the model. I will come back to the parameterization in a bit, but let me first talk about where those priors come from. We don't actually want to operationalize the complex similarity patterns. Instead, we prefer to read pairs of similar characters off existing resources that by design encode the same similarity patterns. For example, for the phonetic prior, that would be the phonetic keyboard layouts. These layouts are designed to make bilingual typing easier, and they are created by pairing each original alphabet character with a Latin character that is perceived as the most similar phonetically. This here is a Russian keyboard layout, and we can see that a lot of the mappings it contains are the ones that we observed in the examples before. But the problem with it is that it's a forced one-to-one mapping. So each key can only correspond to a single character from each alphabet, and each alphabet character has to be paired to a key. So this would result in those layouts containing arbitrary pairings of leftover characters and characters not paired to anything. For the visual prior, we use the Unicode confusable symbols list. Confusables are symbols that can be made virtually indistinguishable in most modern fonts, and originally this list has been compiled to test the font's vulnerability to script spoofing attacks. For example, here I replaced the first two characters in the ACL web page address with identical-looking Cyrillic ones, and while the link looks the same to a human, its Unicode representation is different, so it wouldn't lead to the correct website. But because this list is so specialized, it contains only nearly identical characters, and it wouldn't cover the whole diverse range of visual phenomena that we can encounter in our data. For example, it doesn't actually contain any mappings between Arabic and Latin symbols because the two scripts are just not similar enough. We incorporate those mappings into the model as the prior and the emission parameters. And our conditional emission distributions are multinomial, so we use the conjugate Dirichlet prior. And encoding a list of mappings in a Dirichlet prior is mathematically equivalent to adding pseudo-counts to the corresponding elements of the emission matrix in training. For mappings where a character is paired with a digraph, we would increase the elements of the matrix corresponding to each of the digraph symbols separately. Coming back to our model, it would be simplest for us to assume that each Latin character is produced by a single original alphabet character. However, that's not really true. We can have an original alphabet character producing two consecutive Latin characters or even producing nothing. So we're not only marginalizing over the latent sequences, we're also marginalizing over the latent alignments between the observed and latent sequences. For our model to learn those alignments, we allow insertions and deletions, which would correspond to the epsilon symbols in the source and target side, respectively. Our proposed model is a cascade of weighted finite state transducers, where the transition model is a character-level n-gram model of the original script, and the emission model is a transducer whose arcs correspond to character substitutions, insertions, and deletions. Because we allow deletions in our model, the length of the latent original alphabet sequence can potentially grow infinitely. And because we don't want to marginalize over extremely long sequences, we limit the delay of every path through the emission model. In our case, delay is equal to the difference between the number of insertions and deletions at each time step, or in other words, the distance from the diagonal in the alignment matrix. We train our model using EM algorithm with a range of tricks to speed up its convergence, like stepwise batch training, curriculum learning, pruning emission arcs. You can find more details on that in the paper. For Arabic, we use an existing dataset of SMS and chat dialogues annotated by Arabic speakers. And for Russian, we collect our own dataset. We start with a list of frequent Russian words, and for each of them, we generate a diverse set of romanizations, which we then use as queries to collect data from social media. And we manually annotate the validation and test portions of the data. We start with the unsupervised model without inductive bias, or in other words, with a uniform prior. And we evaluate the model's performance using character error rate, so lower is better. The uniform prior model does not work well, but incorporating a visual prior already gives a substantial improvement. We don't have a visual prior for Arabic because, as I mentioned, the confusables list didn't contain any Arabic-Latin mappings. The phonetic prior works better than the visual prior, most likely because it contains mappings for more characters and because users tend to prefer phonetic substitutions over visual overall. Finally, for Russian, we can combine the visual and phonetic mappings in a single prior, and this gives us our best performing unsupervised model. We compare those results to a supervised skyline, which would be the same model trained on the parallel data from the development set. And we can see that while none of our unsupervised models can outperform the supervised one, the introduction of this inductive bias substantially shrinks the gap between the two. We also experiment with other baselines. Unsupervised neural machine translation model trained on characters actually works pretty well for Russian, but completely fails for Arabic. And we also compare to the commercial hand-engineered systems for decoding romanization, which we are yet to beat. To sum up, we propose a noisy channel unsupervised finite state model that converts informally romanized text back into its original orthography. We present a dataset of informally romanized Russian, and we show that the unsupervised model can induce a substantial amount of supervision from the similarity priors in the absence of parallel data. And interesting directions for future work would include operationalizing the notion of character similarity so that it's continuous rather than binary, and allowing separate emission parameters for different users or groups of users. That's all. Thanks. If you have any questions, I'll be happy to answer them in the Q&A sessions or over chat. Thanks for watching.